Hi, welcome back to the channel. In this video, I am going to discuss Cambridge International A-Level Physics Paper 5, Planning, Analysis and Evaluation, May June 2025, Paper 54. Are you ready? Grab your paper. Let's start answering the question. Right, so now I'm going to start with the first question first. Look at this ball. That's the ball. It's dropped onto an inclined thin metal sheet as shown in Fig 1.1. The angle between the sheet and the horizontal bench is theta. The height of the point of contact of the ball and the sheet is z. The horizontal distance traveled by the ball when its points contact with the sheet and the bench is d as shown in Fig 1.1. It is suggested that d is related to theta by the relationship given here, where v is the speed of the ball as it makes contact with the sheet, g is the acceleration of free fall, and p and q are constants. Where plan a laboratory experiment to test the relationship between d and theta. You have to be extra careful. This is about d and theta. And you have to draw a diagram showing the arrangement of your equipment. Explain how the results could be used to determine values for P and Q. In your plan, you should include first the procedure to be followed, the measurements to be taken, the control of variables, the analysis of the data, and safety precautions to be taken, as well as the additional details that you want to add. Right, so I'm going to follow my format right here. Now, this is a diagram that I drew. Right, I have a meter rule and there's a set square here as a safety precaution to make sure that the meter rule is vertical when I do my measurement of the height of the ball. And I have a retort stand because I want to clamp the sheet at a certain angle, and the angle theta is being measured by protractor, and the distance d where the ball hits the bench will be measured by another meter rule, right? And then I have a shallow bucket which I filled with 5 cents, so to avoid the ball being bounces off the bench, right? So this is my format. I start with the independent variable. My independent variable would be theta because it is easy to vary it. And the dependent variable would be the distance. Variables to be kept constant is my z. I make sure that the height z, right, from where the ball hits the sheet, right, and measured from the bench is constant all the time. And I'm going to talk about that later. So I'm going to start with my method or my procedure. My methods. First method, I always ask the examiner, refer to my labeled diagram. So I say, set up the apparatus as shown in diagram. And then after that, because I'm going to vary my independent variable, which is theta. So I'm going to tell the examiner that how am I going to measure my theta? So theta is measured by protractor. Done. And then the third step, right, the height z. How am I going to measure it? Okay, because height z, because it depends on the theta. So you have to think it logically. When there is theta, is the angle between the horizontal or the bench and the sheet, right? The height z is not so I would say that the value of height z is not so high. So I am going to use, because it all depends on the theta. If you start your theta with a small angle, then your height z would be quite small. So I would say that my height z, right? Or I can write z, not a problem. Height, but I'm going to use height z because all the symbols are being explained. Height z is measured by vernier. I'm going to use vernier calipers because it is not so large height. And then after that, I'm going to measure the height of the ball from the sheet, right? Because the ball is dropped from a certain height, which is measured from the sheet. Okay, so I'm going to measure height of ball from the sheet is measured by meter rule, the one that I clamp beside the ball, right? And then I am going to tell, because I'm going to make sure that the Z is constant. So I'm going to measure the speed where the ball hits the sheet. So that is a V. Could you see that? V is here. This is the V where um this is a V right here. You can see that this is PV squared sine 4 theta. So I'm going to write that. I'm going to say that V, since V has already been explained, I am going to calculate V because there's no apparatus in the lab that I can use to measure the V. So I'm going to say that V can be calculated by equation. If you remember the kinematics equation, there are three kinematics equation. If you remember, I'm going to write that down here, right here. Okay, here you can actually use S equal to UT plus half GT squared, because after all, ball is being dropped for a certain height. You replace the A with gravitational acceleration, or you want to use V squared equals to U squared plus 2GS, or V is equal to U plus GT. I try to not using the time because I don't want to measure the time. So I'm not using the time. So I am using the second equation here. But the initial speed or the initial velocity of the ball is equal to zero because the ball starts from a certain height and the ball is at rest. You hold the ball. Right. So I am going to use V can be calculated from, since I'm going to use a V equal to V squared. Okay, I'm going to use this, yeah. V squared equal to U squared plus 2GS. This U squared is equal to 0, so V is equal to square root 2GS. So I would say that V can be calculated by V equals to square root 2GS. And I have to explain every symbol that I wrote here. And I'm going to put a comma here where G is gravitational acceleration. And you can also put the value 9.81 meter per second squared. And S is the height. S is the height of ball from the sheet, the one that I measured earlier. Right, and then I would say that because this is a relationship between theta and D, so I'm going to tell that how the D is being measured. D is being measured by a meter rule, another meter rule, which lies horizontally on the bench. And after that, I'm to say that because this is theta, my independent variable is theta, so I'm going to tell that experiment must be repeated because after all, this is physics experiment. Experiment is repeated with different theta to obtain different D values. I'm done. Now move on to analysis. Right, analysis, there will be 3 marks given for analysis, so you need to write 3 points here. Analysis, this is my analysis. So analysis, you just tell what kind of graph that you want to plot. So I'm going up to the relationship right here. So you could see that this is a graph, the relationship between D and theta. So I'm going to take up all of sine 4 theta. Therefore, if I plot the graph of D against sine 4 theta, PV squared over G would be my gradient, and Q square root Z would be my y-intercept. So make things easier, I'm going to plot exactly a graph of D, a graph of D against sine 4 theta, right, is plotted. Okay, so I'm going to put a bracket here, sine 4 theta. 4 times the theta. Wow, that's just a big value here. Sine 4 times the theta bracket is plotted, done. And you have to predict what kind of graph that you would get since the relationship is already been given. So I said that if a straight line graph with, because this is not the graph that passed through the origin, with y-intercept of q square root of z is obtained, relationship is valid. And last part, answer the question. Okay, you might wonder, what question is that? Right, explain. This is the question you have to answer. Explain how the result that you use could be used to determine the value of P and Q. So I'm going to write that down. P, okay, I'm going to write gradient first. So you have to see that PV square over G is equal to my gradient. That is why to find the value of P, just cross multiply. It is the gradient multiplies by G divided by V square. And we are done with that. And then for y-intercept, Q square root of Z is equal to y-intercept. We are supposed to find Q. Q is equal to y-intercept divided by square root of Z. And done with analysis part, quite easy. Right, and the last part is our safety precaution and additional detail. Safety precautions and details. So I'm going to write down the first one because I'm using protractor. Most of the protractors that we have in the lab is a clear protractor. So if I want my readings to be even clearer, observable on the protractor, so I'm going to put a white piece of paper behind my protractor when I take the reading of theta. So a white piece of paper is placed behind protractor when theta is measured. And the second safety precaution, remember I drew it on my diagram and I told you earlier, I put a set square here. What is the function of the set square here? The function of the set square is to make sure, because I'm supposed to use the vertical meter rule to measure the height of the ball. That will affect my V value. So that is why I need to make sure that my meter rule is 90 degrees or perpendicular to the bench. That is the function of a set square. So set square is placed beside meter rule to measure to make sure meter rule is vertical. And the third one, I say that, okay, you know, right, when you conduct the experiment, look at the diagram given here. So the ball will hit the thin metal sheet first before bounces off to the bench. And you know, bench, right, is made of wood. Right, most of the bench in our physics lab, right, our benches are made of woods. So that is why the ball, depending on the ball could be easily bounces off. And the measurement of D could not be made as accurately as possible because when the ball bounces off, how are you going to measure the D, right? So you cannot measure something that is moving. So that will give you uncertainty in the D measurement. So that is why I place a shallow bucket. So the bucket that is not so high, just in case the ball hits the sides of the bucket. and then I fill in with some fine sands into the bucket in order for the ball to stay still once it hits the bench, when it's dropped to the bench. So I say fine sand. Okay, is spread evenly inside a shallow bucket and placed on the right side of a ball to prevent, okay, or to provide friction to the surface of the ball and to avoid ball bounces bounces off the bench. Bounces. Okay, bounces. Okay, where's the bounces off the bench? Done. And then the fourth, okay, safety precaution. I did mention that Z would be variable to be kept constant during the experiment, but how am I supposed to make Z as constant as possible? You know, when the data is being adjusted, right? You see, because you want to measure the value of Z, let's say at maybe 5 cm, for example. And then when the theta is being adjusted, okay, getting bigger and bigger, and of course the Z value will change. So that is why I need to make sure, how am I going to make sure that the Z is constant? I put a mark on the bench, right? And I also change the value, okay? So I also change the mark on the bench in order for the Z to remain constant. So since I have the initial value, so when the theta is increasing, I put another new mark on the sheet, not on the bench, so sorry, on the sheet to make sure that the Z value is always constant. Right, number 4, so I say the mark on the sheet is changed as theta is increased. The mark on sheet is changed when theta is increased to ensure Z value is always constant. And number 5, right, I say that the height of the ball falling, because I want my speed, my V, to be constant as well. In order for the V to be constant, I need to make sure, because after all, V depends on 2GS, the height of the ball falling, right, towards the sheet, right? Ball fall, height of the ball, okay, from the sheet, okay? So the height of the ball from the sheet, right? You have to make sure that it is constant all the time. But how are we going to make sure that it is constant? You use your meter rule at the side there to check, right? So I've said that the height of ball falling, or I put here S, is kept constant by using a meter rule. Clamp beside the ball to ensure that the speed is always constant. Okay, to ensure V is constant. Now, number 6, which is the last one, you know, sometimes when you fill in sand into the shallow, especially shallow container, when the ball bounce, okay, towards the sand, right? So some of the fine sands might be going into your eyes, right? You see that? So that is why maybe one of the safety precaution, you might want to wear goggles to protect your eyes. So I would say use goggle or wear goggles to protect the eyes when the ball drop uh, to the shallow bucket containing sand. Now, okay, I would like to add one more to my variables to be kept constant. That is my V. And we are done with the first question. Right, feel free to comment below if you have any suggestions or any hesitation or any doubts. Right, now let us continue with second question. A student investigates the relationship between the luminosity of a star and its mass. The student obtains data of relative luminosity lambda and relative mass mu for 6 stars, where lambda is equal to luminosity of star divided by luminosity of sun, and mu is equal to mass of the star divided by mass of the sun. It is suggested that lambda and mu are related by the equation lambda is equal to k mu to the power n, where k and n are constants. A graph is plotted of log lambda on the y-axis against log mu on the x-axis, determining the expressions for the gradient and y-intercept. Now, since they told us that this is a log graph, so you have, from the equation given, you have to do some modification, mu to the power of n. So I'm going to log both sides. Log lambda is equal to log k plus n log mu. Do you see that? So I would say that, okay, this is my y-axis and this is my x-axis. Therefore, n would be my gradient and log k would be my y-intercept. Now, gradient of the graph, very simple. Just use a little bit of math here. Gradient of the graph is n, and the y-intercept is log k. We are done. Now, B, values of mu and lambda are given in table 2.1. Calculate and record the values of log mu and log lambda in table 2.1. Include the absolute uncertainties in log mu. So log mu, you have to include uncertainty. Normally, I would do this. I put plus minus in between first. And then I do my calculation for a log mu first because, right, for log mu, to find the absolute uncertainty of log mu, I need to stress out here that I am going to follow whatever that you have learned in AS. In AS, you learn in the second chapter that the absolute uncertainty must be denoted in one significant figure. So I am going to follow that. And I'm going to put one significant figure for the absolute uncertainties in log mu. Now, look at the first one. How do I get the absolute uncertainty of log mu? You look at the value 4.6. 4.6 is an average value of mu, which spread between two extremes. What are the two extremes value? You take 4.6 plus 0.4, that is the upper extreme value, 5.0. And the lower extreme value, you take 4.6 minus 0.4, which is 4.2. These are the two extreme values. Right, so your mu can be spread between 4.2 to 5. Right, now, in order for you to avoid some careless mistake, I did a lot of careless mistakes, so I wanted to avoid careless mistake. So I'm giving you some simple tips here, right? So you can use upper value or the highest extreme value and the average value. So I'm going to use that to find my absolute uncertainty of log mu. How do I do that? Since this is about log, I'm going to use the log larger value, which is 5, minus the log average value, which is 4.6. Now I'm going to do that, log 5 minus log 4.6. And I am going to round it off to only one significant figure, which I rounded off to 0.04. What about the second value? Second value is also the same. Save your time. You just add 0.4. Here you will get 5.8. So you just use the upper extreme value and the average value. So log 5.8 minus log 5.4, and you get the uncertainty, which is 0.03, one significant figure. And what about this? I am going to use log, this is 8.8, log 8.8 minus log 8.4, and I got 0.02. And the next one, 11. 11 plus 1, the upper value, extreme value is 12. So you use log 12 minus log 11. So you get 0.04. And okay, the next one, 16 plus 1, you get 17. You use the upper value, 17, log 17 minus log 16, and you get 0.03. And the last one, 18 plus 1, yeah, which is 19. The upper extreme value is log 19 minus log 18. So you get 0.02. Once you have done your calculation of absolute uncertainty in log mu, right, you can calculate your log mu. But if you want to calculate your log mu, just use the average value. The average value is the one that's shown here, 4.6. So when you log 4.6, and one more thing, a tip here, reminder, when you denoted your value together with its absolute uncertainty, make sure that your readings follow the decimal points of your absolute uncertainty. Look at log mu for the first one. I have 2 decimal points. That is why log 4.6, you have to round it off to 2 decimal points, which is 0.66. Log 5.4, I round it off to 2 decimal points, which is 0.73. Log 8.4, round it off to 2 decimal points, which is 0.92. Log 0.04, 2 decimal points. Log 11, I round it off to 1.04, 2 decimal points, remember. And log 16, I round it off to 2 decimal points as well, which is 1.20. Lastly, log 18, I round it off to 2 decimal points, which is 1.26. And we are done with that. Now, lambda, on the other hand, okay, if you want to know how many significant figures you are supposed to put for lambda, right, you look at your lambda value. Okay, log lambda is on your right-hand side. Right, it's on a y-axis. So if you want to know, okay, whether I'm supposed to put it in terms of 2 or 3 significant figures, I would suggest you to put in 3 significant figures. Why? Because on the y-axis, given all the values are in 2 significant figures, but this is 3.8. You look at example that I want to give you here, or you look at the one, okay, I point here, okay, 3.8, 3.824, this is 3.81, 3.82, 3.83. That's 3 significant figures. So I would strongly suggest you to round it off to 3 significant figures. So the first one is 2.70, log 500, log 800 is 2.90, log 3,200 is 3.51, log 7,000 is 3.85, log 25,000 is 4.40, and log 38,000 is 4.58. Done. Now, since we are done with our table, so we have to plot the graph of log lambda against log mu. Include error bars for log mu. Now, I want you to see that log mu is your x-axis. That is why your error bar must be horizontal error bar. And plot all the lines, and together with your worst acceptable line. So your best fit line, I believe you know how to plot it. Make sure that all the points lie close to the best fit line. And your worst fit line, if you start from the front of the error bar, you have to end at the back of the error bar. If you start from the back of the first error bar, you have to end at the front of the last error bar. And make sure that the worst fit line that you draw crosses out all the error bars in between. And we are done with that. And then after that, determine the gradient of your line of best fit, include the absolute uncertainty in your answer. So I'm going to find best fit first. Best fit. MB, my gradient of best fit. So I put in two values here. My best fit is a green color line. So I have my coordinates. I have my two coordinates, 1.29, 4.68, and the other one is 0.7 and 2.8. The green color line represents my best fit. So I'm going to use different colors here so that you can see it better. But in your real exam, you can only use one color, which is your pencil. Right, so I'm going to use that, my best fit gradient. So y2 minus y1 divided by x2, 1.29 minus x1, 0.7. And here I got 1.88 divided by 0.59. And I put as many significant figures first, 3.1864. 1, 2, 3, 4, 5. I put 5 significant figure. It doesn't matter because that's not my final answer. So for my worst fit, so I'm going to put M worst. So I have two coordinates as well. One is 1.3, 4.64, and the other one is 0.74, 3.04. So I'm going to find the gradient. My gradient would be y2 minus y1 divided by x2 minus x1. And my gradient of worst fit is 1.6 divided by 0.56. And I got 2.8571. Now, if you want to include the absolute uncertainty for your gradient, very simple. You just take a larger value minus the smaller value of gradient. So round it off. I'm going to follow AS syllabus as well. I'm going to round it off to one significant figure, which is 0.3. So I'm going to put 0.3. And remember what I told you? The gradient value must be the best fit gradient, and it has to follow the decimal point of your absolute uncertainty. So I'm going to put one decimal point, 3.2. And the next one, determine the y-intercept of the line of best fit. Include the absolute in uncertainty in your answer. Now, I want you to look at the graph again. The graph does not start from origin. So if the graph does not start from origin, you cannot read off from the graph. What you have to do is that you have to do your substitution. Now, I'm going to find best fit first. What do I mean by substitution? Substitution means that you know that this is a straight line graph. So you follow the straight line equation, which is y equals mx plus c. You get what I'm trying to say? Now, find my y-intercept, C best, my gradient must be the best fit. And the two coordinates that I took from my best fit, one of the coordinate that I used just now, 0.7 and 2.8. You can use other values, but make sure that you don't use the points that you used to plot here. Why? Because not all the points lie on the straight line. You use the points which are already on the straight line. Use the coordinates which are already on the straight line. Now I get a value, and this is 2.8. My gradient of worst fit, my gradient of best fit is 3.2, and x is 0.7. Let me put a bracket here, 0.7. A bracket here. This is blue, so I'm going to stick to blue. Plus y-intercept of the best fit. The y-intercept of the best fit will be 2.8 minus 3.2 times 0.7, and I got 0.56. Now, worst fit. So same thing, y equal to m, but this has to be the worst fit gradient, x plus y-intercept of the worst fit. The points that I used was 1.3 and 4.64. So here would be 4.64. Gradient of the worst fit, I round it off to 2.9. So 2.9 times x value 1.3 times y-intercept of the worst fit. So y-intercept of the worst fit is 4.64 minus 2.9 times 1.3. And I got 0.87. Right, and now to find my absolute uncertainty of my y-intercept, take the larger value 0.87 minus the smaller value 0.56, and I got 0.3. Round it off to one significant figure, so I'm going to put plus minus 0.3, and I make sure that my y-intercept is the y-intercept from the best fit, and I round it off to one decimal point, 0.6. D, using your answers to A, C part 3 and C part 4, determine the values of K and N. Include the absolute uncertainties in your values. You need not concern with the units. Thank God, you don't have to worry about a unit. Right, now, for part D, right, when they ask you to combine from part A, look back at part A. Gradient is equal to N. Y-intercept is equal to log K. So we're going to use that gradient. So I'm going to say that N is the gradient. So it's easier to determine. And you have to include the absolute uncertainty. So N is equal to 3.2 plus minus 0.3. And we are done. Just copy the value from the gradient. 3.2 plus minus 0.3. You need not concern with the unit, so just ignore the unit. So log K is equal to your y-intercept, but I want to find the K value. So K is equal to 10 y-intercept. 10 to the power of y-intercept, anti-log. So since I need to get the value of my absolute uncertainties for K. So I need to find the best K value, then the best y-intercept, which is 0.56, and I got a value, which is 3.63, and then my worst K value is 10 to the power of 0.87. Worst fit y-intercept, so I got 7.41. Wow, that's a big difference there. Right, so the delta K would be the bigger one minus the smaller one and round it off to one significant figure, and I got 4. So plus minus 4 is quite large actually. Actually, it's quite large. It is not so accurate, I would say. And then my K value, since there is no decimal point, so I have to round off my best K value to one significant figure or one without decimal point, which is also 4. So I would say that my K value is quite inaccurate. So if you plot it nicely, maybe because I plot it digitally, so maybe the thickness of my pen and that causes inaccuracy, one of the inaccuracies as well, right? And then maybe the points that I took wasn't exactly on the straight line. So whenever you plot the graph, make sure that the pencil that you use is as sharp, right? Not so blunt, and then not so thick line that you draw, as thin as possible, and make sure that the line is exactly on the points that you took. Right. E, the mass of the sun is 2 times 10 to the power 30 kilogram. The star Alpha Centauri B has a value of lambda of 0.46. So we have to determine the mass M of Alpha Centauri B. Now, look at, for this question, okay, I want you to look at, I'm going to scroll up. I want you to look at the second question again. Could you see that mu is equal to mass of the star divided by mass of the sun? So mu can be calculated from here, but it also depends on this equation. And therefore, I'm going to use that equation, right? I'm going to write down the equation first. Lambda is equal to K mu to the power of N. Right. Now, since the lambda is already been given, which is 0.46, and the value of K, I'm going to use the best fit value. Everything also best fit unless the question asks you to find the absolute uncertainty, then only you bring in your worst fit. Mu, I don't have the value of mu, so I need to find to the power of N, and I put the best fit 3.2. And mu to the power of 3.2 is equal to 0.46 divided by 4, which is equal to 0.115 mu 3.2. Now, no choice because we need the value of mu. So I'm going to log that. 3.2 log mu is equal to log 0.115. Now, log mu, I get a value of log mu first. Log mu is equal to log 0.115 divided by 3.2. So, mu is equal to 10, right? To the power of log 0.115 over 3.2. And get a value of your mu, I put it in terms of 4 decimal point, 0.5087. Now we definitely know that mu is equal to mass of the star divided by mass of the sun, which is already been given, which is 2 times 10 to the power of 30. Cross multiplication is needed right here. 0.5087 is equal to mass of the star B divided by 2 times 10 to the power of 30. So mass is equal to 1.02 times 10 to the power of 30 kilogram. So that's my answer, 1.02 times 10 to the power of 30 kilogram. So that's the end of the discussion. I hope you gain benefits here. And don't forget to like and subscribe to my YouTube channel if you want more updated past year question discussion. And please do comment below if you need any help on any past year questions or any topic and you want me to do a YouTube video just for you. Just comment below. Thank you very much for watching. See you in my next video. Bye.